In the previous session, we could cover up to the power spectral density of the ASK signal, which is what we can see on the screen right now. So we'll proceed from there. Next, we'll look at the demodulation of the amplitude shift keying signal. So what do you mean by demodulation process, right? So we are trying to recover the waveform, all right, and the making a decision about the symbol, right, or the bit which has been sent. That is what is called as ASK. Sorry, the demodulation, right? So this includes the recovery of the symbols or the bits from the waveform. Received. Okay. So anyway, we know that there are basically many methods of the demodulation process. So the first technique that we are going to see is the coherent method of the detection. So this is coherent detection. Right. So let's look at the block diagram first, then we'll discuss about process. So since this is coherent, we know the meaning of coherent. What do you mean by coherent? There is a carrier signal. Carrier is available, right? So carrier is denoted by phi1 of t in our modulation process. So it's understood that this is available on the receiver side, right? Okay. We have the received ASK signal. Let's try to denote that by x of t. This is coming from the antenna. As the first process of demodulation, this is passed. This is given to a product modulator. Right? So the product modulator takes the phi1 of t as input. So this is under root 2 by TB into this is cos of 2 pi FCT. Okay, this is the product modulator. So we'll notate, we'll put the product symbol over there. Obviously, this is going to be given to what is called as an integrator. So the next block that we are going to write here will be an integrator circuit. So this is integral 0 to t, right? Whatever function that comes as input into dt. Okay. After this integration, the result will be sampled out at the desired sampling duration. So that's why we'll write a sampler here. This will be moved and sampled at every t equal to t. Okay, so we get now every time you sample, you're going to get a single value. Let's call that as a sample. So let me give a name here. Let me call this the sample which is coming at the output of the sampler by the name x1. Right, now we'll give this sample to a decision making device. So how the decision is made? Anyway, it's based on some threshold. So this threshold value will be decided by the constellation diagram, signal constellation diagram, which we had used. Okay, so that is VTH equal to, let's quickly refer to the constellation diagram of ASK, where you can see that there is a threshold we already defined in the previous session, where one of the symbol is S2 equal to 0, other symbol being S1 equal to root of EB, the central point, right? So the midpoint, that is root of EB by 2, is considered as the threshold, right? So the same thing we are going to use now as a threshold. So this is root of EB divided by 2, right? Depending on the x1, first the x1 is compared with the root of EB by 2, and once we compare that, right, if the x1 is greater than the threshold, right, the declaration of the result happens in the following way. Let me write it over here. So this is going to be decided as 1, right, in such a case that okay, anyway, V threshold is known. I don't have to write the V threshold once again. So let's simply write if x1 is greater than V threshold. Okay, the symbol will be decided as 0 if the x1 comes lesser than the V threshold. So that is the decision process. All right. So received signal gets multiplied using a product modulator. You multiply with the carrier signal, right, or the basis function, then integrate it over over a period. So take a sample, get a sample, compare it with the threshold in a decision device, and make a decision. That's all. Okay, so it's very straightforward process. Let's try to write it in 1 or 2 sentences. So the received So we have a received signal that is denoted by x of t. Okay, so that signal is going to be received signal x of t is so whenever we do the multiplication, it's also multiplication by the product modulator. You can call it by a technical term that is cross correlated. Okay, so received signal x of t is cross correlated with a local in the sense this is generated inside the receiver. Okay, it's not collected from the other part of the circuit or the transmitter. Okay, so I can write locally generated by 1 of t, right? So this output is right. So you take a product and integrate. That's what is actually considered as the cross correlation. If you remember the process that you might have studied in maybe DSP, signal processing, right? Where you study the concepts related to the autocorrelation and the cross correlation. So this cross correlation is nothing but integration of the product of two different signals, right? So first signal is x of t, second signal is phi 1 of t. Take a product and integrate. That's why it is cross correlated. So once you have the cross correlation done, you have the output available that's getting sampled at every TB seconds, right? So the results are sampled at every t is equal to capital T, right? To get the sample, to get the sample values denoted by x1. All right, so the x1 denotes the samples denoted by x1. Now, this x1 is compared with the threshold root of EB by 2, and the decision will be made like this. Right. So x1 is compared with B threshold equal to root of EB by 2 to make the decision. That is output equal to 1. We'll write the same thing. Okay. So if x1 is greater than the threshold value, it's going to be 0 if the x1 is lesser than B threshold. So simple process of doing a decision. Okay. Now, so we looked at the power. We looked at actually the waveform also, how it's going to look like. And one point which we considered when we looked at the requirement is that what is the probability of error? So this is actually very important concept when it comes to the digital communication technique of uh, any method, right? Maybe FSK, PSK, ASK, or even other coherent, non-coherent, right? Techniques. Any technique you consider, you should know the probability of error of each of the techniques. So that reason, we are going to deal with the calculation of the probability of error of most of the cases. Okay, so first, let's do the probability of error calculation of ASK. Probability of error of ASK. Okay, just recall what was covered in the college. Are they uh, dealing with the complete derivation of the probability of error, or they're just mentioning the results? What is the equation? So to answer this, we'll start with the derivation. So let us say the probability of error is calculated on which side, transmitter side or receiver side. It has to be receiver side, correct? Because receiver is the one which is tending to make an error, right? Okay, so let's start like this. So we'll write let x of t be the received signal. Okay, now so x of t will be normally whenever you consider the practical channel, there is the probability of error coming into picture. If your channel assumed is ideal, then ideal channel will not alter your signal. Whatever is sent from the transmitter will reach the receiver, right? So it means, since we are calculating the probability of error, the received signal will actually include whatever was sent and whatever uh, modifications are performed on that channel, sorry, on that signal by the channel, right? So two parts will be there, correct? So okay, let x of t be the received signal in the form, we are trying to write the format, that is x of t is equal to, so what was sent, so we denoted the sent signal as s of t, okay? To this s of t, you have the noise getting added. I denote the noise by W of t. Anyway, I'm going to write this. This is for symbol 1, because only when symbol 1 is transmitted, you have S of t being generated. Otherwise, it is 0. So when it is 0, right, it 0 will be added with only the noise. Okay, that is W of t. This is when you send the symbol 0. Are you okay? So this is what you are going to receive in case of the practical channel. So this is valid for 0 less than t less than or equal to t. All right. Now, so that means let's try to write the various terms. The terms are like this. So the W of t is actually called as the white Gaussian noise process, right? So there are various types of processes available to represent the noise, because see, noise is completely random. You cannot write a equation for noise, right? But you by using the statistical properties like mean, covariance, variance, etc., by using them, you can try to guess a PDF of that probability density function, right? So now we are assuming that, right, this follows a Gaussian process. It's a Gaussian noise, right? So whenever you say Gaussian noise, you have to specify what is the mean and what is the power spectral density, right? So it's a Gaussian noise with zero mean. Mean is zero, right? In the sense you have all the positive and negative samples of the noise coming with equal probability, so that when you take the mean, it becomes zero. Okay, mean and power spectral density, PSD, as N naught by 2. Okay, then let's also try to denote okay, let's try to calculate the x1 now, right? Because I have to take a product of this x of t with the phi 1 of t and integrate, right? So this implies the output of correlator, that is nothing but x1, because you sample it, right? So the sampled value is equal to integral 0 to tb, incoming signal is x of t, right? Into, you multiply that with the basis function, that is phi 1 of t. Since you are doing the correlation, this is okay, right? So this is what you get x as x1, correct? So now you see this x of t. Let me try to split this and write so that this becomes easy for us to understand. So this is equal to integral 0 to tb. What is x of t? That is s of t plus the w of t into the phi 1 of t dt, correct? So this is nothing but integral 0 to tb. This is s of t into phi1 of t dt plus integral 0 to tb, this is w of t into the phi1 of t dt. Right now you see, after this integration, the t will not be there, t will vanish, the variable of integration will vanish, because you are substituting for substituting the value 0 to tb for the variable t, right? So anyway, there is a product and you integrate. So let's call the first integration, result of first integration by s1, and the second integration by a name w1. So let's say this is x1 equal to this. Call this as equation number 1. All right. This is when 1 is transmitted, correct? So this implies, I'll write this is x1. So I'll write here, therefore, if 1 is transmitted, then I'm writing like this, because S1 is there only when you are sending uh, uh, 1, right? Otherwise, it's just going to be the noise. Right, W1, correct. So now when I say S1, what is the value of S1? If you remember, I think we wrote it somewhere when we discussed about so you see, S1 is nothing but it's denoted as the root of EB, correct? That's what the energy based representation of symbol 1. So anyway, before substituting that, I'll try to make a comment here, right? So here, right, where okay, let's write what is S1. So when I say I'm sending S1, that is represented as a signal component, where S1 equal to root of EB uh, is the signal component, and W1, right, is the noise, and right, it is the noise component, right, where this is at the output of the sampler, correct? Because x1 is the signal value you get at the output of the sampler. Okay, now let's bring the probability concept into picture. So have you heard of the word that's a random variable? Okay, so will you be able to uh, tell me what is a random variable, or even if you give me an example, that's fine, or even if you tell me why do you need a random variable is fine. Yeah. See, when I say there is a variable, maybe I denote the variable as A. Okay. When I say A, you can assign any value to that. Like maybe when you write a code or something, you can assign A equal to 1, A equal to -1, right? A equal to say pi, right? Etc. You see, you are trying to assign the random, you are going to assign the values randomly to the variable. Right, that is already when I which means when I say there is a variable, right, it's already going to be assigned with the random values. But a variable, there is a difference between variable and a random variable. Okay, now let me see, let me look at the one example so that that becomes clear for you before I make the actual statement here, right, which includes the random variable. Okay, now let's take an example of tossing a coin 2 times. All right. So you toss the coin twice. So let me try to write the sample space of the result. So what are the possible results? You may say when I toss a coin twice, I may get 2 heads, right? Head and tail, tail and head, and the tail and tail. I hope you are fine with this. Okay. Right. Now No, sample space is not random variable. Okay, I'll bring the word random variable into picture. Let's say this is when I toss the coins, I'm doing some experiment. Okay, but I will try to measure the result of an experiment by using what is called as the random variable. Okay, for example, uh, okay, let me say that my experiments results I want to analyze by using what is called as the number of heads. Okay, number of heads in during my experiment. So let me define that as a capital X. Now you see this is a random variable. So what are the possible answers? Number of heads. I want to count the possible number of heads that comes whenever you toss a coin two times. What are the possible answers? You see, when you get TT, there are no heads. Okay. When you get the HT or TH, right? That means one. When you get HH, you have two. Okay. Now you see this result is getting converted into a randomly. Now you see you are not assigning this, right? So previous example, when I said A equal to 1, I am assigning that in according to my requirement, it may be in some program. Okay. This is what you assign A equal to 1. Once you assign A equal to 1, unless and until you change in the program like A plus plus or A equal to say C divided by D, right? Do something like this, it will not change. Right. So that's what is the example of a simple variable. Now you see, anyway, I don't want this. I'll erase this part. I will justify why do I call uh, the capital X as a random variable. Now you see, this value X depends upon the experiment's result, which is random, correct? Are you okay? So you toss a coin, right? What do you get? You don't know. But the results are assigned directly to a variable X. Again, this is not necessarily the count of heads only. You can even count something else, right? Like the number of tails, right? Depends on what experiment you are doing, right? Again, so the values here for this experiment only three values: 0, 1, and 2. But right, if your experiment is slightly different, like maybe throwing two dice altogether, right? You will have a larger values coming up, right? Maybe some of the two dice, right? Whenever you throw, whatever comes, that's a different uh, experiment. So you see, in that case, the capital X will be completely different. Are you okay? Right. Now you see this X converts the result of a random experiment into a set of random numbers or a numerical value. That's all. It can be real, integers, or anything. Are you okay? So because of that reason, so such variables which take random values depending upon some experiments. Okay, right? They are called as the random variables. Right? Are you able to differentiate between the variable and a random variable now? Okay. Now, so why I use the word random variable? Because now we are actually considering this W1, which is a random, right, process. I am trying to take a sample of that. So the number you are going to generate, you are going to generate a number now, right? When I say I am trying to write the value of W1 in this equation, some equation I have where I want to substitute the value of W1. But I know that W1 is actually a sample of some process, right? And that process itself is a random thing, right? So because of that reason, now I'll make a statement like this. All right. So this W1, I'm talking about a W1. Also, the W1 is a sample value, a sample of the random variable. Now you see, I'm going to write the okay, I'll give an example. I'll slightly extend this example which we considered just now. So you see here, there is a set, maybe S, denoted by all the possible outcomes. X defines, right, all the possible outcomes for a given experiment, provided experiment is defined like counting the number of heads. Now, so what are the samples of X, right? The samples of X could be 0, 1 or 2. So each one of the sample will be called as a xi, small x. Small x denotes sample of the capital X. It's one entry out of the capital X. Any one entry. Okay. The small x could be 0, small x could be 1, or the small x could be 2. Right? So this is called as, okay, I'll write in bracket. This is the sample of capital X. Right. Now you see, I'll make the proper statement where this is my small letter w. Okay. This I'll write like this just to denote that this is small letter. So small w1 is the sample of a random variable. See, this is capital W. Now it makes sense. You see, capital X, small x, right? The similar notation I'm trying to use here. The capital W1 is the random variable, which can take any possible value, out of which at the moment of reception of your signal, whatever noise is included with your received signal, that is a small W1. Are you able to distinguish now? So what is small w1? Small w1 is equal to your sample here, individual value. So the capital W1 is all possible values of noise, right? So whatever values the noise can taken for a given channel, right? That's represented inside W1. So W1 could be, you can write 1.1 minus 2.5, 8.96, 100 points, something like that. You have a huge set, right? Set of values that W1 can take. Out of all those values, any one of the value will come, right, as small letter w1 whenever you sample your signal. Correct? Because at that moment, because continuously channels properties are varying, you have variation in the values of small w1, which is taken from one of the possible values present in the capital W1. That's all. Okay, just look at this example I have given over here, right? That makes everything clear to you. Over here, this one. Okay, all right. Now, let me go back. So in the next step, so variable, I have written till here, this is still the variable W1, random variable W1. Okay. Now, let's say small x1, right? You see, because of there is a randomness present in the received signal, right? The small x1 which we have written earlier becomes one of the sample value of all the possible outcomes of the capital X1. I'll bring it to picture. You see here I am using the small x1, correct? Small x1, you can try to relate that. Now you see this is completely random. W is completely random. So some fixed signal plus a random signal makes this also random, isn't it? Are you able to understand that? So in equation number one, I'm talking about that. So there is S1, which is a fixed signal, let us say. Okay. Because W1 is random, randomly picked a sample out of capital W. Correct? will be substituted over there for small w1. So s1 is fixed. So you will understand that w1 is random now. So when you add a random number to a fixed number, the result will definitely be a random number, right? So small, I can make a statement now. Therefore, small x1 is a random sample of a random, another random process, which is capital X1. Are you okay? Right. So that's all. That's where the randomness comes into picture. So because of which we are going to get the values other than sent value, and the value will be present anywhere on the phi axis of the constellation diagram. Okay, right. Okay, before that, let me complete this sentence which I tried to write. Uh, this implies, right, the small letter x1 is a sample of, again, since the w1 is assumed Gaussian, the capital X1 which I'm going to write now will also be Gaussian, because it's a process which controls the randomness. All right. So sample of, I can write Gaussian. Now I write a short form RV, right? Say that, so the Gaussian random variable denoted by, let's try to denote this as a, say, capital X1. So now we try to write the expected value. Okay, there is what is called as a mean, because whenever we have the random uh, variables present in our equations, we cannot write actually the proper equation governing the properties of that variable, correct? Because it is random. So what are the parameters you can calculate for a random variable, right? I think you might have studied in engineering mathematics somewhere, right? One thing is expectation, that's a mean, then variance, standard deviation, etc. Those things can be calculated for any randomly varying quantity, correct? So this is small x1 is a sample of the Gaussian random variable x1. So this means I can calculate the expected value or the mean. Expected uh, value of x1. So how do you denote that? This is E of x1. So E of x1 has to be the expected value of, what is x1? It is small s1 plus w1. Okay, sorry, I made a mistake. This w1 is not small. I'll write it properly. Okay, so this is s1 is small plus this is w1. Okay, that's a capital W. Now onwards, I'll write a small w like this. Okay, and capital W like this. So just for your reference. Okay, this means now, just now we made one statement that what is the mean of W1, right? Again, this is an assumption. The assumption mentioned, in the assumption we mentioned that, I'll just show you. Right, okay, so you see what is a mean? Zero mean, right? So the mean, in the sense, it is expected value. So whenever I write capital W, it has a mean equal to 0, right? So now the expected values, I can write it as E of S1 plus the expected value plus the expected value of W1. So W1, I know that it's going to be 0, right? For a signal, right, the expected value itself represented by its value of, that is EB, root EB, right? Plus second one has 0. So you can say that the expected value of the x1 is a root of E. All right. Similarly, we will calculate what is the variance. So this is the mean. So also this implies the variance of x1 is equal to how much it varies. Okay, so it's a measurement of the variation of any variable, right? So now we are trying to calculate the variance of that x1. Okay, so therefore the variance of x1 is equal to, it's a very similar process. So you calculate variance of s1 plus w1, that is equal to, you split it. Okay, variance of s1 plus the variance of w1. So s1 is a well defined signal, okay, for which you have an equation. So unknowingly there is a, the chance of varying that signal is zero. There is no chance of the signal which is going to vary, right, without our knowledge, because it's predefined. Its variation is predefined by an equation. So variance of s1, right, is zero. Something which is already known to you has zero variance, but the noise has some variance. Again, you can see the assumption we made, that is n naught by 2. So the variance of x1 becomes n naught by 2. Okay, all right. Now let us try to write the PDF, right? The PDF is going to define what is the probability that you receive a specific value x1 provided you transmitted either 0 or 1, knowing value, some known value you send. Okay, so let's try to write that. This means, okay, so we'll write in this way. Therefore the conditional PDF probability density function of x1, given that the, I know that I'm sending symbol 1 only, because so far whatever discussion we did, it's for symbol 1 because there is s1 present. If symbol 0 was sent, the s1 is not there, right? Only the noise will be present. Okay, so right now what I'm writing is with respect to symbol 1 being sent. Okay, so conditional PDF of x1 given that the symbol 1 is transmitted, right? This means, let's try to write this. So we give a notation. PDF is denoted by small letter f. Which random variable you are talking about, you'll write it in the capital format as a suffix, that I'm talking about x1. Now you tell me the receiving component, right? If I try to write the capital X1, right, the possible values of X1, maybe they can be 0 or 1, right? X1 could be 0 or 1, which means what? How do you denote this? This is small x1. So that means the PDF of the capital X1 of, you write, you see I write small x1, means I am receiving any of the small x1 given that 1 was sent. See the meaning of the notation. I think you have already come across the conditional PDFs in mathematics, correct? So this is the same representation. Okay, so if you are able to recall, I'll proceed further. So, right, so that is small f, notation for a PDF, capital X1 as a suffix indicating that that's the random variable which we are talking about. Inside the bracket, whatever you write, sometimes this might be written as x1 divided by 1. Okay, that's also fine inside the bracket. That's a notation for, I'm trying to measure the probability of getting or receiving x1, small letter x1, given that 1 was sent. So that's a condition, right? So divide by 1 is a condition, which means you are very sure that I sent symbol 1, but what is the probability that you get a 0 or 1? So x1 can take 0. You can, when you expand this further, maybe you can put a 0 bar 1 here, indicating that you are calculating the PDF of receiving a 0 when you sent 1. Or you can even write 1 bar 1, saying that inside the bracket you write 1 bar 1, indicating that what is the probability that you are trying to receive a 1 when 1 was sent. Okay, so right now we are not calculating a specific value because I'm trying to write an equation, PDF, right? So this is equal to, if you remember, this is a Gaussian random variable. All right, so that is, you try to recall the general equation. Okay, so that is 1 divided by, this is a general equation for Gaussian variable, that is root of 2 pi sigma square into exponential of, this is minus of whatever is your sample, that sample, whichever you want to calculate. If it is x1, you write x1. Okay, x1 minus the expectation of x1. All right, so that whole square divided by, this is 2 times sigma square, right? So actually this variance is there, right? This itself is the sigma square. So I actually missed that earlier. So the variance itself is that. Otherwise you can write the variance itself over there. Instead of sigma square, you can write a variance. All right, so maybe in some other books, I'll give other notation as well. So the E of x1, that will be represented as mu x, right? Standard notation for mean is mu, right? So you may find that as well. Okay, right. So now what we do, we'll substitute the values to get an equation. Okay, so the equation for this specific case is like this. That is equal to 1 divided by, you see I'm substituting, this is root of, let me substitute, then we'll simplify. 2 pi sigma square is n naught by 2, okay, into exponential of, this is minus of x1 minus, you see expectation of x1 was root EB. We already have calculated, whole square divided by 2 times, this is n naught by 2. So you see 2 cancels here as well as here. So the final answer that we can directly write here is equal to 1 divided by root of pi into n naught into e to the power, the same thing where we are going to substitute this 1 divided by root of pi n naught e to the power minus of x minus root of EB the whole square divided by n naught. All right, I'll call this as equation number 2. That's nothing but fx1 of x1 given that 1 was sent. Right, so this whole discussion was about I sent a 1, but what you are going to receive. Okay, you are trying to calculate that probability. Okay, that's the PDF, conditional PDF when 1 was sent. Okay, right, now I'll write similarly. So similarly, what you are supposed to consider now, what happens when you send a 0? Okay, similarly, when the 0 was sent, right? When I send a 0, what happens to the x1 now? This implies small x1 becomes equal to, let's just go back to check the equation once again. Which equation I'm right now talking about? I'm talking about this equation number 1. Okay, so we can see that equation number 1 becomes x1 is equal to s1 plus w1, right? So s1 plus w1, in which s1 is 0 now, correct? So this is simply becomes equal to w1, right? And let's try to write the expectation now. This implies e of x1, the expected value of this becomes equal to 0 because it is noise, right? So this itself I can write, which is equal to expected value of w1. Also, tell me what happens to, therefore, the variance of x1 in this case becomes equal to n0 by 2. Are you fine? So I'll directly write this implies f x1 of receiving x1 provided 0 was sent. Okay, now you see this is equal to 1 divided by same equation. I'll substitute. This is 2 pi. What is the sigma square? It is n0 by 2 into the into exponential value of minus of, there is x1 minus, you see where the mean is 0. All right, so into 2 times n0 by 2. This is a minus outside, whole square. Okay, so that means this is equal to 1 divided by pi root of pi into n0 exponential of minus x1 square divided by n0. Solve this equation number 3. That's the equation for x1 provided x1 bar 0. Okay, now we understood that. Okay, this is the PDF. So equation 2 will be the PDF for receiving any sample for small x1, maybe 1 or 0, provided 1 was sent. Okay, similarly, equation 3 represents the PDF for receiving any sample small x1, provided you send a 0 from the transmitter side. Now you tell me what is the how do you represent the error? What is an error? In the sense, when 1 was sent, when you, because our intention now is to calculate the probability of error, right? Before that, I need to understand what is an error, right? So error is like something like when 1 is sent, receiving a 0, right? At the same time, error is also is going to happen when you send a 0 and you receive 1, right? 1 was sent, received 0, it's an error. 0 was sent, 1, you receive 1, again that's an error. Correct? Okay. Now let's try to understand an equation. Let me try to write an equation over here. Okay, let me try to define the error now. As discussed, let me try to define. Right. Therefore, I'll write the decision is error if okay, let's just separate and write. So if symbol 1 was transmitted, but the x1 falls in the region denoted by z0. Anyway, I'm going to copy the previously written constellation diagram once again here. so that this becomes clear. Okay, so you see, we are talking about a region Z0, which is over here. Okay, so let me just copy this. Is it okay? So if at all the signal symbol 1 was sent, but on the receiver side, the x1, the sampled value of received signal after the cross correlation, if it falls in this region denoted by Z0, that means it is error, correct? So that's what that's the point. At the same time, whenever I send 0, and on the receiver side, the small letter x1 falls in region Z1, that's also error. Right. Okay. Now that makes many things very clear to us. So I can make another statement now. So that means this implies, now again I'm talking about one only, right? That symbol one was sent. So this implies the symbol error occurs if I can say x1 is less than the threshold. What is the threshold? That is root of EB by 2. Okay. Similarly, right, also I'll write the straightforward statement now. So when the 0 was transmitted, error occurs if, so error is going to occur if, what's the condition? The x1 is greater than root of EB by 2. Correct? Are you okay with this statement? Okay. Now let us try to denote directly we are calculating the probability of error now. This implies the probability of error when the symbol 1 gets transmitted, right? That is right. We try to denote that as probability of error when 1 is being transmitted. Okay, PE of 1. This is nothing but the probability that the x1 falls lesser than root of EB by 2. Correct? Probability that x1 is lesser than root EB by 2, provided the symbol 1 gets transmitted. So when 1 was sent and you receive x1 lesser than root EB by 2, that is going to be the error for probability, probability of error when 1 is transmitted. Are you okay? Okay, let's try to write an equation now. So you use the PDF to do this. So recall what we had studied in engineering mathematics related to the random variables concept. this is nothing but I'll write an equation. You see, I'll go back to the just now. Okay, so you see all the way from minus infinity till root EB by 2 you can come, right? That means the what is the region of x1? X1 can be anywhere from minus infinity till root EB by 2, correct? That's the chance. So I need to do the integration because when you integrate the PDF, you get the probability. This is what is basic, right? So I have a PDF with me. You need to integrate to get the probability, correct? So that's why I'm doing the integration. This is it. So therefore, this is nothing but this is equal to, I'm trying to do the integration all the way from minus infinity till the boundary, that is root EB by 2. So anywhere your x1 falls, that means it is an error, right? So using that, I'm doing this. So therefore, this is integral minus infinity till root of EB divided by 2. So write the function, that is fx1 of x1, given that 1 was sent, the variable is x1, dx1. So small letter, okay? Right. So this is what I need to do. So let us substitute. We already have the equation with us. Simply substitute. Whatever constant I have, I'll try to take the constant outside. So this means this can be written like this is equal to, I have a constant value that is 1 divided by root of pi n naught integral minus infinity to root of EB by 2. Okay, exponential of minus of x1 minus root of EB equals square divided by n naught dx. All right, so let's try to simplify this by substitution, right? So let me put y is equal to x1 minus the root EB divided by, I use a root n naught here because I can see that there is a so that this becomes a complete square for me. Okay, so this implies whenever I try to do the dy, okay, so what is dy? Can you tell me? When I try to, because I need a dx1 to be substituted in the equation, because equation has, my original equation has dx1. I need something to be substituted over here. So when I do the dy, dy is equal to dx1 divided by root n naught. That's my substitution. So this implies what you can substitute for dx1 is equal to root of n naught into dy. That's what this is going to come and occupy this place when I substitute everything. Okay, now let's also do the calculation. The x, actually dx1 varies all the way from minus infinity till root EB by 2. Correct? So I need to change the limits definitely. Okay, so let's change the limits now. So this implies, let's try to substitute. So when x1 is minus infinity, y is also going to be minus infinity, because minus infinity minus root EB by root n naught doesn't make any change, correct? So we'll make that. So therefore, when x1 is equal to minus infinity, this implies the y will also be minus infinity. So lower limit will not change, but upper limit might change now. So x1 is equal to root of EB divided by 2. So that means what happens to the upper limit. Upper limit is nothing but now this implies y is equal to what is x1? Upper limit of x1 is root EB by 2. Okay, this is root EB. Have to divide outside. So this is y is equal to root of EB whole divided by 2 minus of root EB. Okay, this is divided by 2 minus of root EB whole divided by, there is root n naught. So this is going to be minus of root EB by 2, and there is in the denominator I have a root n naught, so I'll take that also inside the root, because numerator also root EB denominator has a root n naught, so can be clubbed together. So I'll directly write the answer. So it's a negative minus half times root of EB by n naught. Right, so this is the upper limit. So now we'll make the changes. So this implies what we were calculating. We were calculating the probability of error of 1, that is equal to, so I have to substitute like this. So there is already 1 divided by, what was the constant outside? Pi n naught, root of pi n naught. 1 divided by square root of, this is pi into n naught. Then I'll do the integration from minus infinity to minus half root of EB by n naught into, right, the whole exponential becomes simply exponential of minus of y squared. Okay, because you see the substitution we made, y is equal to x1 minus root EB by root n naught. That's what is my substitution. So because of that, I'm going to get this. Okay, so that means I can write now, this is minus infinity to this number. Okay, this is exp exponential of minus y squared. Then I need to substitute for dy, right? Sorry, dx. What is dx? Dx is root n naught times dy. So you can see this root n naught and this root n naught cancels. All right, so that means this is equal to 1 divided by root pi integral, this is minus infinity to minus half minus 1 by 2 root of EB by n naught. This is simply exponential of minus of y square dy. Okay, now this is one of the very standard function called as error function. Okay, so anyway, you don't have to solve this, right? There are some error functions which are standard and predefined. So this itself, 1 divided by root pi minus infinity to half of root of EB by n naught, right, into e to the power minus y square dy itself is, right, the half of the error function ERFC of half root of EB by n naught. Okay, so this is the probability of error of 1. Okay, so this is what we are going to get when we try to calculate the probability of error of 1. Okay, now similarly, I'll hold on to this. Maybe I think this is equation number. This is probability of error of 1. So we'll hold on to this equation, maybe I think equation number, right? So now we'll do the calculation for probability of error of 0, right? So I can write therefore, similarly, I'll not write what is it because we are very familiar. PE of 0 is nothing but this is the probability that what happens to x1, probability of our x1 is becoming greater than root of EB by 2. Under what condition? 0 was transmitted. Okay. So whenever you send 0 and the received sample x1 is more than root EB by 2, that's the error corresponding to 0, right? So I can write 0 gets transmitted. All right. Okay. So this means, let's try to do the similar calculation now. So you see, this means from where to where you should integrate. Can you tell me the limit of the integration? Consider this diagram and the symbol falls in region 1 and the symbol sent was 0. Where do you expect? You can consider the previous equation, because previously I was looking at region z naught. So identify the range of z naught, and the answer was minus infinity till root EB by 2. That is region z naught, everywhere, all the way from minus infinity till root EB. Now I want the error with respect to 0. So if your sample x1 is in region z naught, that is not an error. So when you send infinity, yes, perfect. Okay, so that's the answer. So this means it's the same. I know that what is the PDF. I need to integrate the PDF in an appropriate region to get the probability. Okay, so this means where do you integrate? Integration from root of EB divided by 2 to infinity. Is it okay? Right. Which function you use? This is f capital X1 of small x1, provided, now you see it is not 1, it is 0. Okay. Provided 0 was sent into dx1. Hope it is clear, right? Up to this. Are you fine with this? The equation. Okay, now we'll substitute. So this is equal to I'll substitute. So just recall, we calculated this is equal to root of phi n naught integral root EB by 2 to infinity, right? This is simply exponential of minus x1 square by n naught, isn't it? Into dx1. So now, according to our similar convention of integration, I need to make a substitution. So you are going to put, say, y is equal to x1 divided by root n naught. So that term becomes complete square, right? I am not considering n naught as it is, root n naught. So that there is x1 square and root n naught whole square. What happens now? So this implies what is what I should put for x1. So this implies dy is equal to dx1 divided by root n naught. So that implies wherever I have dx1, that is equal to root n naught into dy. So need to calculate the limit. So first let me calculate the upper limit, which is straightforward. So when I say x1 is equal to infinity, what happens to y? Y is also infinity because infinity by root n. That's not going to change. But when x1 is equal to, it is root of EB by 2, this implies just calculate what is y. So that means y is equal to x1 by root n naught, right? So that is root EB by 2 whole divided by root n naught. Correct? So the root n naught and root EB can be clubbed together as this. This is half root of EB by n naught. Fine? Right. Okay. So let us do the substitution. Let's complete that. So this implies on the left hand side, what I have probability of error when 0 was transmitted. So this is equal to now 1 divided by root of pi n naught 1 divided by root of pi n naught into integral 1 divided by root of pi n naught into the integral. So lower limit, as you can see, this is half of root of EB by n naught till infinity, e to the power or exponential of minus y square into dy into dx1. So dx1 is root n naught into dy. So once again, root n naught cancels, right? I'm going to get the very similar expression now. Like the previous case, let's try to write that. So this is equal to 1 divided by root pi integral half root of EB by n naught. Start from this limit and goes all the way to infinity, e to the power or exponential of minus y square dy. This is nothing but, actually, you see the limits have been negated and their positions have been exchanged, which means there is no change. It's once again the same function, right? So that is also equal to half of error function of 1 by 2 root EB by n naught. That is probability of error of 0. So this is, let me call equation number 5. Okay, now, so what is the total probability of error is my question. It's not the probability of 0 or probability of 1. Okay, so to calculate that, symbol 1 occurs with the probability P of 1. Okay, and symbol 0 occurs with the probability P of 0. Right, that's what we understood so far, right? In the sense, how do you generate, right? What is the probability of generating the symbol 1 on the receiver side? So we have no idea. We call it as a equiprobable case, right? So assuming equiprobable events generating 0 or 1 on the transmitter side, that implies you see, this is not error. Probability of occurrence of 0 is equal to probability of occurrence of 1 is equal to half. Okay, probability, how probability, how the 0 occurs, same way 1 also. Probability of generating the symbols is assumed to be half. Are you okay? Right. This implies, now you see we are trying to calculate the total error, right? That implies we call it as actually average probability of symbol error, right? This implies, I'll write this statement, average probability of the symbol error. Let's try to denote that as PE. So PE is equal to, this is how you calculate in the probabilistic way of calculation of average is right like this. That is probability of 0 into probability of error when 0 was sent. Okay, that's the first term, plus the probability of 1 into the probability of error when 1 was sent. This is the total probability. Okay, average probability. So what is P of 0? That is half. What is P of 0? Half. That's again half, right? That's the same equation. So half into 1 by 2 ERFC, error function of half root EB by N naught. That's my first term. Plus once again, P of 1 is half into half error function of 1 by 2 root EB by N naught. So 1 by 2 is 1 by 4. So second, this thing also 1 by 4. 1 by 4 plus 1 by 4 is 1 by 2. So I'm ultimately going to get the same answer, that is equal to 1 by 2 into error function of half of root of EB by N naught is the total probability of error when you use the amplitude shift keying in your transmission. Okay, so that's the derivation which I was talking about whenever we want to represent the ASK for the modulation process. Okay, please check if you have any doubt with the whatever we discussed so far, right? I can explain, otherwise I would like to move further. Any doubt? No, okay, all right. So ASK is complete. Let's move further. I'll start with the next one, that is PSK, phase shift key. Right. Now, as we know now, the PSK, we have to use two different waveforms to represent binary symbol 1 and binary symbol 0. Okay. So let S1 of t is equal to, so very similar expression you can see here. Magnitude is represented in terms of energy and the time duration. So root of 2 EB by capital T root of 2 EB divided by capital TB times, this is cos of 2 pi FCT, so 0 less than or equal to 1, not 1, sorry, T, small letter t, less than or equal to TB, right? So this is going to be used whenever our symbol transmitted is 1. Okay, so symbol 1 means I'm trying to represent this using this notation. That is S1 of t equal to this. So S1 of t equals to 2 pi FCT, 0 less than or t less than or equal to TB, right? This is for the symbol 1, right? Similarly, let me write also, let me say S2 of t is equal to. So if you remember the waveform which we had drawn earlier, what is the difference between the S1 of t and S2 of t? What should be the difference? Phase changes. By how much? What's the change in the phase when you have two symbols? No, when you have two symbols, 360 by 2. When you have four symbols, 360 by 4. Correct? So now it should be 180 or pi. Correct? So that's why S2 of t will have the same amplitude, same frequency, but there is a change of what you call phase that is represented by pi. So I will be writing the same thing. So this is root of 2EB divided by TB into cosine, same function, 2 pi FCT, no change in the frequency, but there is a change of phase, that is pi. So this is 0 less than or equal to T less than or equal to TB, right? This is going to be used whenever I'm going to send the symbol 0. Okay, now you see, right? Actually, there is, I can write the S2 of t in a slightly different way. What is cos of 180 plus theta? If you remember, there is a property. So I'll write this. So cos of pi plus theta can be simply written as minus cos theta. Correct? Do you remember? So I can use this property now, right? So let me use this property so that I can uh, convert my above equation of s of t, which should look very similar to my function. Okay, that's what. So let me try to. Just a second. It's my. Just 1 second. My system is hanging now because it's continuously running since morning 5 o'clock and it's very hot, getting very hot. Okay, sorry for the inconvenience. Just 1 second. It's actually hanging. It's not able to identify what I'm writing. So only cursor is moving, but I'm not able to erase that. Sorry. Okay, this came anyway somewhere. I'll write with this same thing. Okay, so this means I can apply this. So you see, there is a two root of just 1 second. 1 second, it's time. 2 EB. Sorry for the inconvenience. It's actually taking some more time. So this is 2. No, it's not right. 2 EB. Can you see? No, right? Two times. It's EB divided by, say, TB. Okay, and right here, maybe let me check right. So this is equal to, I'm trying to write, this is root of 2 times EB divided by TB. All right, so this is equal to, let's try to write, root of 2 EB by TB. So cos of 180 plus theta, I can see a cos of 180 plus theta where this is my theta, right? So the 2 pi FCT itself is a theta form, correct? So I can write minus of that. So this is minus of root of 2 EB by TB into cos of 2 pi FCT, right? So this is when 0 less than or equal to T less than or equal to TB for the symbol 0, right? So compare S1 and S2 of T, they are negative of each other, right? I'll just show you the S1 of T now. So just verify. S1 of T and S2 of T are negatives of each other, that's all. Which means, now you tell me, now I'll ask you a question. How many basis functions you require to represent this, right? So if I have something like, there is a signal, like this is say plus x1 and this is like minus x1, how many axes you require to represent that? Only this axis, right? I don't have any height, right? Only one dimension you keep moving. Either S1 that is coming over here and S2 which is coming on the other side. That's all. Correct? So that indicates that I don't need what you call as multiple dimensions. So dimension in the sense it's once again the same point, right? We don't need many dimensions or many basis functions. So how many basis functions do we require? So that means the answer is only one. Is it okay? Right. So this implies, I can write one statement here. This implies one basis function is required, right? So let us try to define that as follows. So let the phi 1 of t, once again I require only one, that's why I'm writing simply phi 1 of t. So therefore phi 1 of t is equal to, so similar notation, root of 2 by tb into cos of 2 pi into FCT cos of 2 pi FCT, right? 0 less than or equal to T less than or equal to TB. Okay, now I understand that when I am sending the symbol 1, I need to multiply this by plus root EB. Okay, and when I want to get, when I want to send the 0, I need this to be negative, right? So minus root EB needs to be multiplied. Correct? So this implies, I can write now. So this implies what is S1 of t? S1 of t is equal to root of EB into the phi 1 of t, right? And S2 of t is equal to, what is that? Minus of root EB into phi 1 of t. Are you okay? Because I have to get the same S1 and S2 which I defined just now. Are you okay with that? Then that means, okay, let me try to write the required block diagram. So how do we generate this? We'll see. So on one side, I'm going to start with a binary wave. How do you represent? That is either root EB for 1 or minus root EB for 2. Okay, so like A and minus A. That itself you take as input and use a product modulator. It's a modulator, product modulator. So to which, since I need only one phi, that is a basis function, simply do this. Okay, so I'm trying to do this now. I'm going to multiply to this with the phi 1 of t equals to root of 2 by TB cos root of 2 by the TB into cos of 2 pi FCT. I multiply this. So that's a product modulator. I know that if it is plus root EB, I get the required S1 of t at the output. And if at all it's minus root EB, what should I get? I should get the S2 of t at the output, right? So it's a very simple block diagram representation for the generation of the PSK signal. So I will simply write the PSA signal. So common name for if the input is binary, the name is BPSK. So don't get confused if you see this somewhere, right? BPSK for binary PSK. Only two inputs, only two symbols are used. That's why. Okay, fine. So that's the block diagram representation of the what you call the modulator. Okay. Now we need to look at the PSD now. Right? So you see what we are using plus root EB and minus root EB format, right? So whenever I have a plus root EB and minus root EB as my input signal, what should be the uh, baseband signals power spectral density? Okay, I'm writing that now. So just recall what we had studied yesterday, right? Since the input has plus or minus root EB as the levels. This is non-return to zero, correct? Non-return to zero, but since you have plus and minus, this is polar. So what do you write? So signal levels, the baseband PSD is denoted by same notation, that is SB of F is equal to, this is A square capital TB into sinc square of F into dB. All right, so this is the baseband PSD. Right, now what I should do in order to get the PSD, right? You have an input multiplied by the phi of t, which means it is going to move to FC and minus FC, right? So that it becomes what? It becomes the band pass, right? So this implies the band pass power spectral density of BPSK, binary PSK, right, is nothing but, now this is SS of F is equal to the same equation. This is 1 by 4, right, times SB of F minus FC plus SB of F plus FC. Same equation like yesterday, but the substitution is of a different SB of F. So the baseband representation is slightly different because what we used earlier is not the same what we are using now, just because of that reason. So previously we used a different signal or the waveform for the signals, but now we are using a different types of rectangular waveform. Okay, now let us substitute. That means this is going to be equal to 1 by 4 into, there is A square TB into the sinc square of FTB, but F becomes F minus FC. So what is F minus FC? This has to be a right shift, isn't it? Okay, so I have a right shift, I have a component that is right shifted, and I also have another component which will be left shifted. Okay, so A square TB into, this is sinc square of F minus FC times TB. This is the first component, plus A square TB sinc square of, this is F plus FC times TB. So this is the equation for the PSD of BPSK. Now, anyway, let us try to plot them. Right, so the not the center, somewhere here maybe. Okay. This is central line, and let me draw the x-axis like this. So if you recall, the how the A square TB look the baseband, that is SB of F looks like. So the SB of F looks like this. So it starts from point. There is no delta function, correct? So it's a sinc square. So it starts from here. It comes to a minimum value, goes and like this. Same thing will be repeated on side. Comes like this, goes to top, and so. Okay, so the highest peak, again, so this comes here, minimum. So the highest peak can be written as the A squared into TB. And the sinc square, so since it is a square function, you can see that this is only present in the first and the second quadrant, positive values of y. Okay, that's the thing. So now this is 0, this will be 1 by TB, this is 2 by TB, minus 1 by TB, minus 2 by TB, and so on. So this is my f-axis. Okay, so that is the baseband. But when I try to write the spectrum, or sorry, the PSD of the band pass, this is how it's going to look like. Okay, that is because the waveform is going to be shifted to right and left. So let me assume that this is say FC, and let me also assume that this is minus FC. So I'm going to get a very similar form, but repeated on both sides. So it starts from here, moves to this point, minimum, a small maximum, again a minimum, and like this. Same thing will be repeated even on the other side, minimum, a minimum, and then small maximum, and followed by the further minimum, and so on. So the same thing we can write on both the sides, uh, positive as well as on the negative side. Okay. Just a second. Once again, it is hanging. Yeah. Okay. So that means this is up, down, increase, decreasing, and so on. I'll write a okay. So this amplitude I can write it as a square TB, right? That's the same amplitude on both the sides. And this is FC plus 1 by TB, because everything moves to either plus FC or minus FC. Okay. So this becomes FC minus 1 by TB. That's the point which is on the left side of the FC. Okay. So this point is minus FC, sorry, FC plus 1 by TB, FC minus 1 by TB. And similarly, on the other side, I have minus FC plus 1 by TB. And the left side of that will be minus FC minus 1 by TB. Okay, so this is minus FC plus 1 by TB minus FC minus 1 by TB. All right, so the two components, whatever we have, let's even write them. So this is a square TV times sinc square of, it's a right shift, right? So this is F minus FC times TV. Okay, similarly, this waveform is nothing but the a square TV times sinc square of F plus FC, F plus FC times TV. Are you okay? Right. So this is the PSD of the PSK, BPSK wave, BPSK type of modulation. All right. Okay. So let us try to stop here for the day. Right. So tomorrow we'll continue from here. Okay.